Welcome back to AI.Code.Cast. Today, we're going to be doing a deep dive into, a real classic problem, the gas station problem. It's one of those algorithmic puzzles that's got a bit of everything, a fun premise, real-world applications, and some seriously clever solutions.
Yeah, it's a favorite for coding interviews too.
Ah.
Really tests your problem-solving skills.
Okay, so let's set the scene here. Imagine a circular route, thing like a racetrack. And along this route, you've got a bunch of gas stations. And each gas station has a certain amount of gas available. And it costs a certain amount of fuel to drive to the next one.
Right. So it's not just the gas you get at each station that matters. It's also the cost to get between them.
Exactly. Now, the challenge is this. You want to figure out if there's a gas station you can start at with an empty tank and make a full loop around the track without running out of gas, kind of like planning a road trip where you're starting with fumes and hoping to make it to the next fill-up.
And the trick is you need to make sure you always have enough gas to reach the next station, not just enough to cover the whole route in total.
Right, because running out of gas halfway between stations, well, that means game over. So how do we even begin to tackle this? What's our first instinct?
Well, the most straightforward approach is what we call brute force. We could literally try starting at each gas station and simulate driving around the track, seeing if we can make it back to the starting point.
So like pick a station, calculate if we have enough gas to reach the next one, then the next one after that, and so on, until we either complete the loop or run out of gas.
Exactly. And if that starting point doesn't work, we move on to the next gas station and repeat the process until we've tried them all.
That seems intuitive enough, but I can already sense there's a catch. Is this brute force method going to be efficient?
Yeah.
Especially if we have a lot of gas stations.
That's a problem with brute force. It can get very time-consuming. Imagine having, 100 gas stations. We'd potentially have to simulate the entire route 100 times.
Oof, that doesn't sound very scalable. We'd be stuck coding all day. There's got to be a smarter way, right?
Absolutely. The brute force approach has what we call O of n squared time complexity, which basically means that the time it takes to solve the problem increases quadratically with the number of gas stations.
Okay, so brute force is out. We need a more elegant solution, something that can handle a large number of gas stations without taking forever. Any hints on where to start?
Here's a thought. Instead of blindly trying each gas station as a starting point, what if we could figure out a way to quickly eliminate some stations that are guaranteed to not work?
Interesting. So like a rule that tells us, hey, if this condition is true, then this station can't possibly be the starting point.
Exactly. And for that, we need to think about what would make a station a bad starting point. What would cause us to run out of gas before completing the loop?
Let me think. Well, if at any point along the route, the amount of gas we have in our tank drops below zero, that means we're stranded, right?
You got it. Now here's the crucial insight. If starting from a particular gas station leads to us running out of gas somewhere along the route, then starting from any station before that point would also fail.
Oh, I see. It's like if you couldn't make it over a hill on a hike, then starting from any point before that hill wouldn't have worked either. You'd still hit that same obstacle.
Precisely. So if we can somehow track our fuel level as we simulate driving around the route, and we hit a point where our gas drops below zero, we can immediately rule out all the previous stations as potential starting points.
That's a pretty clever optimization. It feels like we're pruning away a whole bunch of possibilities without actually having to fully simulate them.
And that's the key to achieving a more efficient solution. Now, before we dive into the specifics, there's one crucial check we need to do right at the beginning.
Okay, what's that? Is it something to do with making sure we even have enough gas to complete the whole trip in the first place?
Exactly. We need to calculate the total amount of gas available at all the stations and compare that to the total cost of driving between all the stations. If the total gas is less than the total cost, it's like trying to drive across the country on an empty tank. It's just not going to happen.
Right. It's like checking your budget for gas before you even start planning the route. So if that initial check fails, we can immediately say there's no solution, no matter where we start.
Exactly. But assuming we do have enough total gas, then we can move on to the heart of the algorithm, which leverages this idea of eliminating bad starting points as we go.
All right, so we've got our budget check in place, and we know we can rule out stations that lead to us running out of gas. What's the next piece of the puzzle?
Well, for that, we need to delve into how we're going to simulate driving around the route and keep track of our fuel level, and that's where things get really interesting.
Sounds like we're about to uncover the secret sauce of this efficient solution. Listeners, you won't want to miss this. Make sure to stick around for part 2 of our deep dive into the gas station problem.
Welcome back to AI.Code.Cast. Last time, we kind of, laid the groundwork for a really clever solution to the gas station problem. We talked about how brute forcing every starting point would be way too slow, and we need to find a way to quickly eliminate possibilities that just won't work.
Right, right. We figured out that if we run out of gas starting at one station then any station before that is also a dead end. And of course, we have to do that initial check to make sure there's even enough total gas for the whole trip.
Exactly. So now let's get into the mechanics of how we can efficiently simulate this road trip and find our ideal starting point.
Okay, let's get into it. So we're picturing our circular track, our gas stations with varying amounts of fuel and the cost to drive between them. How do we translate that into something we can work with algorithmically?
We can think of this like a game where we move from station to station. At each station, we add the gas we find there to our tank, and then subtract the cost of driving to the next station.
So it's like we're keeping a running tally of how much gas we have as we go. Makes sense. But how do we actually keep track of this in our algorithm?
We'll use a variable, let's call it current gas, to represent the amount of gas we have at any given moment.
So at the very beginning, current gas would be 0, since we're starting with an empty tank, right?
Exactly. And then we need another variable to keep track of our potential starting point. Let's call that start.
Got it. So start is like our current guess for which gas station we're testing out as our starting point. We'd probably initialize that to 0 as well, assuming the first station is a possibility.
Right. Now here's the process. We start simulating our road trip from the station indicated by start. At each station, we update current gas by adding the gas available at that station and then subtracting the cost to travel to the next station.
So it's like we pull up to a station, fill up our tank, and then immediately drive to the next one, seeing how much gas we have left when we arrive.
Exactly. Now here's where things get interesting. As we go through each station, we need to check our current gas value. If at any point it dips below 0, that means we've run out of gas before reaching the next station.
And that means our current start value wasn't the right one.
Game over.
Right? Not quite game over,
Right.
but it does mean our current start is incorrect. Remember that crucial insight we discussed earlier. If starting at a particular gas station leads to running out of gas, any station before that would also lead to the same problem.
Right. It's like heading that insurmountable hill on our hike. Starting from any point before it wouldn't have made a difference. So what do we do in our algorithm when current gas goes below 0? Do we just give up?
Not at all. This is where that optimization kicks in. When current gas dips below 0, we know our current start is wrong. So we simply update start to be the next gas station, the one we failed to reach. Reset current gas to 0 and continue our simulation from this new potential starting point. So we're essentially jumping ahead, skipping all those stations that we know wouldn't work. That's so much faster than checking every single one.
It is, and we keep repeating this process, driving along the route, updating our fuel level and adjusting our start position whenever we run out of gas.
But what if we go through all the gas stations and never find a starting point where current gas stays above 0 the whole way around? Does that mean there's no solution?
Not necessarily. Remember that initial check we did to make sure the total gas was at least equal to the total cost. If that check passed and we've gone through all the stations, then our final start value is actually the correct starting point.
Wait, really?
Yeah.
How does that work? It feels like we just kept running out of gas and adjusting our starting point. How did we suddenly find the solution?
Think about it this way. If we've tried every possible starting point and we only run out of gas sometimes, it means there must be a starting point where we don't run out of gas. And because we only adjust start when we run out. If we've reached the end of the list of gas stations, that last start value must represent a path where we never went below 0.
So we're basically using the fact that we know there's enough total gas to deduce that the last station we reach without running out must be the correct starting point.
Yeah.
That's pretty slick.
It is. And because we only go through the list of gas stations once, this solution is much more efficient than the brute force approach.
Okay, this linear time solution is blowing my mind.
Yeah.
But you mentioned another way to approach this problem, something about working backward from the end using suffix sums.
Yes, that's right. It's a completely different way to think about the problem, and just as efficient as the one we just discussed. Want to hear about it?
Absolutely. This is AI.Code.Cast after all. We've got to explore all the angles. Listeners, buckle up for part 3, where we'll delve into the suffix sum approach to the gas station problem. Welcome back to AI.Code.Cast for the final lap of our gas station problem deep dive. We've already explored a really neat solution that simulates the journey and cleverly eliminates bad starting points, achieving that impressive linear time complexity.
But as we hinted at, there's another equally powerful path to the finish line, the suffix sum approach.
All right, suffix sums. You've been using this method. So let's break it down. What's the core idea here?
Instead of focusing on where we start the journey, imagine we look at where we end.
Okay, I'm intrigued. How does knowing the end point help us find the right starting point? It feels a little backward.
Think about it this way. If we can find the station from which we can reach the end of the route with the maximum amount of gas left over, wouldn't that also be the ideal starting point?
I think I see what you're getting at. If we start at that maximum leftover gas station, we're guaranteed to have enough fuel to complete the whole circuit, right?
Right.
Because we already know it gets us to the end with extra to spare.
Exactly. It's like finding a spot on a hiking trail where you can coast downhill the rest of the way. Starting there ensures you never have to struggle uphill. And that's where suffix sums come into play.
Okay, so how do suffix sums help us find that maximum leftover gas station? I'm still wrapping my head around how those two concepts connect.
A suffix in this context is just a portion of our route, starting from a particular station and going all the way to the end.
So like if we have 5 gas stations, a suffix could be just the last 2 stations or the last 3 or even the whole route itself, right?
Yeah, precisely. And the suffix sum in our case represents the net gas available minus the cost to travel for that specific suffix. So it's like calculating how much fuel we'd have left if we started at a particular station and just drove straight to the end.
So we'd calculate the suffix sum for every possible suffix, starting from each station going to the end. That seems like a lot of calculations.
It might sound like a lot, but it's actually very efficient. Remember, we're aiming for a solution with linear time complexity, just like the previous approach.
Right. We don't want to fall back into that O of n squared trap of checking every single combination. So how do we find the maximum suffix sum efficiently?
Well, we can do this with a single loop through our gas station data. We initialize 2 variables, max suffix gas to keep track of the maximum suffix sum we've encountered so far, and max index to score the index of the corresponding station.
So at the beginning, both of those would probably start at 0, right? Like we're assuming the first station is our best guess.
Actually, since we're working backward this time, we initialize them to represent the very last stations. Like we're standing at the finish line and working our way back.
Yeah, that makes sense. Starting from the end and working our way back to the best starting point.
Yeah.
Okay, so we've got our variables set up. What's next?
Now we loop through the stations in reverse order, starting from the last one and working our way toward the beginning. In each iteration, we calculate the net gas gain for the current suffix, which includes the current station and all the stations after it, and add it to a running total.
So as we move backward through the stations, we're considering longer and longer suffixes, and our running total represents the net gas gain if we started at that particular station and drove to the end.
Exactly, and in each iteration, we compare our running total to max suffix gas. If the running total is greater, it means we've found a new maximum suffix sum. So we update both max suffix gas and max index to reflect this new best starting point.
And so like we're constantly keeping an eye out for the station that gives us the biggest gas surplus when we reach the end of the route. And once we've gone through all the stations,
our max index variable will hold the index of the station that corresponds to the maximum suffix sum, and that, my friend, is our optimal starting point.
So to recap, this whole suffix sum approach boils down to finding the station that gets us to the end of the route with the most gas to spare, and using that as our starting point. We're guaranteed to complete the entire circuit without running out of fuel.
Hmm.
Mind blown.
It's a surprisingly elegant solution, and just like the simulation approach we discussed earlier, it achieves that coveted O of n time complexity.
Okay, so we've got two fantastic solutions, both equally efficient. It's almost like picking between two equally delicious desserts. But is there ever a reason we might prefer one approach over the other?
That's a great question. While both methods have their strength, the simulation approach might be easier to adapt if we had additional constraints in our problem, like a limited tank capacity or variations in fuel consumption between different cars.
So if our road trip involved a fleet of vehicles with different fuel efficiencies, we might lean towards the simulation approach because it allows us to model those nuances more easily.
Exactly. On the other hand, the suffix sum approach could be advantageous if we're dealing with preprocessed data or if we need to find multiple valid starting points. Imagine if we wanted to know all the stations that would allow us to complete the loop, not just the most fuel efficient one.
So it really depends on the specific details of the problem we're facing and the kind of information we're looking for. No one size fits all solution. Just different tools for different jobs.
Precisely. And that's the beauty of computer science. Often there are multiple paths to the same solution, each with its own unique insights and advantages.
Well, this gas station problem has been an incredible journey. We started with a simple question about finding the right starting point, explored the pitfalls of a brute force approach, and then uncovered two incredibly efficient solutions.
And hopefully along the way we've sparked some inspiration for our listeners to tackle their own algorithmic challenges.
To all our AI code casters out there, keep those coding brains engaged, and remember, the world of algorithms is full of fascinating problems waiting to be solved. Until next time, happy coding.
Happy coding.